Hello and very welcome to this video. In this video we will look at the memorandum for practicum 3, that's MOW217, the 2023 module, practicum 3, and this video is specifically made for the MOW217 students, but anyone wanting to watch the video is obviously more than welcome. So my name is Dr. Lucas du Plessis. I'm a senior lecturer at the University of Pretoria in South Africa, and I teach the module Manufacturing and Design. It's a module that the undergraduate mechanical and industrial engineering students have to complete as part of their studies, undergraduate studies, and I did not mention, but I work for the Department of Mechanical and Aeronautical Engineering. So what you see on the screen is a CAD rendering, a CAD model of the Shigley-Haller gearbox. I've got separate videos explaining the gearbox, and what practicum 3 was all about was creating or dimensioning the views of the side profile. I'm hovering over one of the side profiles. There are obviously two of them, one on this side, and if I just rotate it a little bit, there's a side profile on this side, and then the base profile, which is this blue profile here at the bottom. So that was what the practicum was about. In this CAD rendering, I've isolated only the two side profiles and the base profile, and what I did here is I showed how these profiles are actually connected to each other, and it's done with these screw inserts, M12 screw inserts. So for that reason, the side profile is obviously tapped in 4 places, each of them, not only the bottom but also the top, and the reason for the tapped holes in the top is because, if I can go back to this image, here you can see I've got a cover plate on top of this gearbox, and that's also secured with M12 cap screws. So alright, so that's the 4 tapped holes. Then each of the side profiles also have a slot cut into the side profile. The reason for that is this gearbox will wind a fishing line. Let me just do this quickly. Okay, so if I go to the inside of the gearbox, you will notice it's on this side, yes. So it's a compound gearbox, and in the last shaft there's a hole, so the fishing line will go through this hole, it gets tied down, and then it leads through the slot to the base of the ramp, where a trolley with Shigley-Haller or Shigley textbooks are pulled up the ramp. Okay, now the reason, there's obviously no need to cut a slot in this side profile here, but for ease of manufacturing and assembly, it does not do any harm to cut the slot in both of them. Then you don't have to worry when you assemble your Shigley-Haller gearbox which one goes on what side. There's symmetry in the design, which makes assembly a lot easier. Alright, so then in terms of the base profile, what happens there is, in order to secure these screw-in fasteners, these red screw connectors, I think that's what they are called, we need access for an Allen key in order to secure the screw inserts. Okay, so that's, I think, self-explanatory. And then also on the base profile, there are tapped holes here in the middle for a certain depth on both sides. Now the reason for that, for those 2 tapped holes, if I can go back here, that's actually well, there was a design revision. The older revision of the Shigley holder assembly is what you see on the screen. So what I had here was tapped holes in 2 locations, and that's for set screws to secure the dowel pin that runs all the way through, and that's on both sides. The reason for the dowel pins are to get good alignment between the 2 side plates. Right, so I did mention the dowel pins, etc. also in a previous video, so you're welcome to have a look there. So as I said, just getting back to the 2 set screws that I had here in this previous revision, I changed the design to have a single set screw in the middle to secure the dowel pin, and to then successfully have access for the screw connector, the 2 screw connectors. So if I can zoom in here, so I've got 2 screw connectors. I need access to those screw connectors, and I need a single tapped hole in the middle to secure the dowel that runs through the base profile. Now what you will notice, and obviously this will be a question, is where's the hole for the dowel? It's not in this initial or stage 1 base profile step file that you see on the screen. The base profile is machined in 2 stages. Stage 1 is simply tapping this M12 hole, or tapping that M12 thread, drilling the 4 holes, and then stage 2 will machine the dowel hole as a precision hole, but we'll get to that in a later video. Okay, so that's why what you see on the screen is simply a stage 1 base profile connected to the side profiles. All right, so with that said, what you see on the screen here is just an import of the base profile. I also imported the step file of the side profile. So if I click on the base profile and I press spacebar, it will disappear from my window here. And similarly, I can make the side profile disappear by selecting it, press spacebar. If I select the base profile again and press spacebar, it will appear again. And the reason why we have it open in FreeCAD is because we want to take measurements, and for that we're going to use the manipulator workbench. And I'll show later on how we go about to decide which measurements to take, because we obviously first need to decide which dimensions we're going to put on the drawing, and then measure those dimensions on the step file and put it down on the on the OCR form. Okay, so let me quickly show you. Yes, here we go. So what you see here is, if I can just zoom out a little bit. So yeah, that's not going to work. Okay, so these are the views for the base profile stage 1, and we need to now dimension each of these views. Okay, so I've deliberately taken out the dimensions, just showing the views. Okay, so if I can run through it, there's basically a front view, a side view, a section view AA, and a section view. That's not very, okay, let me do this. That's the section view BB. Okay, so those 4 views we need to dimension for the base profile, and then for the side profile, there's a front view, section view BB, a side view, and a section view AA. So those 4 views for the side profile. Okay, and what the OCR form looks like. So let me do this again. So if we scroll to the top, yeah, so this is the base profile front view. base profile section AA, base profile top view, base profile section BB, and then side profile front view, side profile section BB, side profile right view, and lastly the side profile section AA. Right, so these are the views that we are now going to dimension. Right, so it's important to note and understand that these profiles come as standard bought out items. You buy them. There are different suppliers in South Africa. You get them from Modular Assembly Technology, and they supply them per meter. You can define what the required length is you want. So in our drawings, we will not specify any of the detail dimensions. We will, however, specify the length of the cross section and the height of the cross section as reference dimensions. Okay, and reference dimensions are obviously put on the drawing for information only, and it's put in round brackets. All right, so but what we will definitely have to specify is the length of the profile we want plus a tolerance. All right, so if we go to our base profile view, we can put the length on any of these views, okay, because the total length of the profile is visible in all three views, but you will put the length only in one of the views. You won't put the length in more than one view because it's unnecessary, okay, and it's also not drawing practice, okay. So with that, what I want to do is I'm going to put the length on this view over here, okay, and while we're here, I'm also going to put this dimension, which is 90 millimeters. I'm also going to put that on this view, and then I will put the height of the profile in this view over here. That 90 and this 30 I'll put as a reference dimension, and what we now need to do is measure the length of the step file to know what is this length, and then we can decide what the tolerance will be. Okay, so to measure the length, we've imported the step file. FreeCAD uses, if you highlight an item in the model tree and you press spacebar, it will disappear. Okay, so I've imported both the side profile which is now visible on the screen, as well as the base profile, so I can make the side profile disappear. Select it in the model tree, press spacebar, click on the base profile, press the spacebar, and it will appear. Okay. Now, in order to take measurements, I prefer using the manipulator workbench. There are other ways as well. Once you open the manipulator workbench, or let me just say, manipulator workbench, you need to install specifically from the add-on manager. So if you don't have it in FreeCAD, you go to Tools, you go to Add-on Manager. It will open all the available workbenches, and then you can search for manipulator. There's the manipulator workbench. Alright, so if you click on it, you can either update, which is I think necessary in my case, but I'm not going to do it now, or install it if you don't have it. Alright. So with the manipulator workbench open, we click on the caliper, we click on the caliper again, and now we have we have two options. We can either use the default probe or to select endpoints. Okay, so then we need to zoom in a lot, or enough rather. Click on that endpoint, zoom out. Now you need to remember which endpoint that you select, but you can do that. Click on that endpoint, zoom out again, and there you can see that the length or the distance is 350 millimeters. Okay. A more elegant way of doing it is simply clicking on the, what you need to do now, what you will notice is that the distance and distance label, these two are now added to the model tree. So if we want to delete that, select them in the model tree and press delete. Okay, so a more elegant way of getting the length is we click on this icon over here, and then we can select any of the edges. Okay, and there you can see the length of that edge is 350, which corresponds to our previous measurement. All right, so with that done, let's now jump to our OCR form. We're going to add the length on this view as well as the reference dimension, and then on this view we're going to put that reference dimension. All right, so with that done, let me just find it quickly. Here's the top view. Right, so here you can see I've dimensioned the length as 350, and I've decided on a tolerance of plus minus 0.5. Now, you will notice, we'll get to the tolerance in a little bit, but you will notice that I've made these leader lines quite long, and the reason for that will become apparent a bit later. I want to specify datums and also form tolerances on these leader lines, and that's the reason for that. You will also note the 90 reference dimension, as well as the 30 reference dimension that we spoke about. Now, I just want to make you aware, if you look at this leader line, whenever there's leader lines crossing any other leader lines, or like in this case the arrow, you will break the leader line. You will not simply draw the leader line all the way through. Alright, and even though it is a freehand sketch, please write neatly. The other important thing is the orientation. So the orientation of the view, we will write so that it is readable in a 12 o'clock orientation or a 9 o'clock orientation. Okay, and this is what I'm referring to here as a 9 o'clock orientation. We will not use 3 o'clock or 6 o'clock. 6 o'clock being upside down, 3 o'clock being orientated clockwise 90 degrees. Okay, so we orientate our dimensions counterclockwise 90 degrees or horizontal. All right. The same is obviously true over here. Now, let's get to the plus minus 0.5. So it's a very loose tolerance, and it's easily achievable with a cut-off machine. You don't have to, and for this application where we have a base profile and two side profiles, there's nothing making contact with this surface afterwards, so we don't have to worry about the length being very precise. Looking at the gearbox as an assembled unit, if I can just rotate it quickly. There's no need to have it very accurate. Okay, so plus you could go for something smaller, but I would not recommend anything smaller than plus minus 0.2, definitely not. Going bigger than 0.5 might also be problematic. Something like plus minus 1 millimeter, it will be visible in your assembly. So anyway, this is my selection. You are welcome to choose anything else, but not less than 0.2. Okay, so with the length of the profile specified, we can then order, if we were to do that, we could order cut aluminium profiles to that length, and we will be able, the manufacturer will be able to deliver what we've ordered. If I can just go back here, because we've got a length, he will be able to deliver that. But in this case, we have additional features that need to be drilled and tapped into this profile before it can be delivered. So it makes sense then to dimension those features that we want machined or drilled or tapped in the profile. Now the M12 tapped holes that are visible here in section AA, those two tapped holes, let's dimension them, and then finally we'll dimension the 4 access holes, but that we'll do later on. Okay, for now we are just going to dimension the tapped holes. If we go back to the supplier website, here you can see that the base diameter or the diameter of this profile, center hole of the profile, actually all 3 holes, that diameter is 10 and it is suitable to be tapped M12. That's why the supplier put this M12 here in brackets. It's suitable to be tapped. Okay, so all we need to do really in order to specify the tapped hole is the depth of the hole. Okay, the depth of the tapped hole. And there's only one obvious choice to dimension that depth, and this is on this section AA view. That's where we will dimension the depth. Alright, so now what we will have to do is measure that depth. Okay, so let's just delete these measurements that we took. Okay, so if I zoom in, I can rotate. Okay, so what I can do with the manipulator workbench, I can let's select the probe. Yeah, let's select this circle then. And we zoom in and we select that circle. Okay, and here you can see the length between the center points of those 2 circles is 20 millimeters. Okay, so that's the depth of the hole. Now what we'll do is we'll go to our OCR form. We'll go to, where was it? I think it was here. Yeah. So on this view, we will simply dimension and show that this is an M12 tapped hole. Okay, and we'll show the depth with a tolerance. All right. Okay, so what I've done here now is I've indicated the depth. Well, firstly, let's just talk about specifying the thread. So I write the word tap M12 by 1,75. That 1,75 is the pitch of a coarse M12 thread, and I put the words in 2 places. So because it will be unnecessary to dimension this tapped hole on both ends of this section AA. Then secondly, what I also did was I indicated the depth. And instead of putting a tolerance, which would also be correct, I simply say minimum 20 millimeters deep. Minimum. I put the word minimum. So if the manufacturer taps a little bit deeper, it's not a problem for us. If you look at the if you look at this assembly, it will definitely not do any damage if that tapped hole is deeper than 20 millimeters, but it shouldn't be less than 20 millimeters. We don't want it too shallow or too short, because then the functioning, okay, and just remember again, this is now revision 0 you're looking at, or revision 1. The revision 2 design is the one with a single tapped hole. So it's important that the thread actually reaches the dowel pin, so that we can, when we tighten these set screws, and in the revision 2 it will be a single set screw, when we tighten that set screw, we want to clamp the dowel to prevent it from falling out. Okay, so yeah, that's then done. So the last features that we need to specify for the base profile are these 4 clearance holes. We need to now specify them. Let's just select these lengths and delete them. Right. And There are different strategies that you can follow to dimension those holes. The strategy that I prefer and that I recommend you use is using a datum reference frame with basic dimensions and a positional tolerance. So in order to do that, we need to decide on our drawing where we're going to define the datums. All right. And what I want to do is specify this bottom surface. Okay, remember we're looking at a line. If we look at the top view, but that line represents a surface. The surface which looks as is shown in the front view. Okay, so the top view, I'm going to specify this surface as a datum, and this surface over here, this surface, this end here, I'm going to specify those two as datums. Now in order to do that, you will remember our length tolerance was very loose. It was plus minus 0.5. So I want to constrain the form deviation, the perpendicularity of these two faces. I'm not so worried about the length. It can vary with plus minus 0.5, but I want the faces to be perpendicular to the rest of the aluminium profile. Right, so I've got two datums, and the third datum for this base profile stage 1, you can select either the top or bottom face. It's okay. An alternative scenario or suggestion or possibility is to select the symmetry plane as the datum. Okay, and that will make sense when we look at the detailed drawing of the stage 2 base profile. Then it would make sense to select not the top or bottom faces as a datum, but the symmetry plane. For this scenario, it would be better actually to select either the top or bottom faces as a datum. So let's do that. Okay, so what you see on the screen is the indication of datum X, and I've selected now the bottom face. Note that the leader line of the datum box is not in line with the dimension. You could have done it like that. The implication is then your datum is the symmetry plane lying between the top and bottom surfaces. The way I've done it here, I indicate the bottom surface. I could also have placed the datum box with its leader line touching this line, this bottom line, and the same is true if I selected the top surface. I could have put the datum box with its leader line on this leader line or on this line over here. So that's datum X. Let's have a look at the other two datums. So I've selected this surface, this bottom surface, as datum Y. Now you can indicate the triangle either as a filled triangle or as an empty triangle. It's easier on my scratch pad to indicate it as an open triangle. Okay, now what I do here is, and note also, ladies and gentlemen, the leader line of the datum box is separated from the dimension line because I want to indicate the bottom surface. If I put it in line with the dimension line, I will be referencing the symmetry plane, which is not what I want to do in this case. Okay, and the same goes for what I've done here. So let's just have a quick look. So I'm saying this surface needs to be perpendicular to within 0,2 relative to datums X and Y. Okay, and the reason for that is, as I said earlier, I have a loose tolerance in terms of length, but I don't want the perpendicularity to be 0.5 millimeter out. I want that to constrain the perpendicularity of this face to 0,2. Now, important, that there are two datums applicable here. It's, in other words, this face needs to be perpendicular to both faces, datums X and datum face Y. The same goes for the opposite side. I specified it as perpendicular 0,2 relative to X and Y. Now, what I did here also is I dimensioned or defined this face as datum Z. So you could have also done parallel 0,2 relative to Z. You could have done that as well. The reason why I prefer the way that I did it here is if datum Z is now out of perpendicularity to 0,2 and I reference this face as parallel to datum Z, it can go out of squareness to the magnitude of 0,4. Okay, so that's a technicality. I think this is, you can do either way, but I think this is more elegant and it more describes what we actually want. So with the datum reference frame then specified, we can dimension the next feature or set of features which consist of these four holes. Okay, and how we will do that is note that we have created this view section BB that runs through two of the holes, and section BB then clearly shows that the hole actually goes all the way through the profile in both locations, and in actual fact in 4 locations. Right, so in doing let's jump right in. So the first thing that we will do is we will measure the diameter of these holes. And in order to do that, we go to FreeCAD, we use the manipulator workbench, and we click on get radius of an arc or circle. We zoom in, we click on the arc, and there you can see the radius is 4, implying that the diameter is 8. So with that done, we can then dimension the diameter of the hole on section BB. So we've got 4 holes, so that's why there is a 4 times diameter 8 plus minus 0,5. So I've selected a very loose tolerance. This is just a clearance hole, as I've said before, for the screw fasteners. Okay, so there's an Allen key that will go in there and locate with this hexagon in order to tighten or loosen the screw fastener. Okay, so for that reason we don't need any sort of tight tolerance. So this plus minus 0,5 is adequate. You can go smaller, but not tighter, that I would recommend, than plus minus 0,2, and plus minus 0,5 is also, I think, at the higher end, or at the maximum scale of tolerancing. Right, then in line, this is very important, in line with the dimension line, we've got a leader line, and here we specify a positional tolerance, diameter 0,4, once again quite loose. You could go a little bit tighter, but I wouldn't recommend anything tighter than diameter 0,2 again, and it's relative to datum X, Y, Z, X being the primary datum, Y secondary, and Z the tertiary datum. Okay, so with that done, we still need to do one more thing, and that is to indicate the basic or theoretical exact dimensions from datum Y and datum Z. It's very important that we do so starting from datum Y and starting from datum Z, because these are the datums that we have selected. If we selected, for example, the top surface, then we would include or show the basic dimensions from that face. But this was our choice, so we need to stick to our choice when we put in the basic or theoretical exact dimensions. Now, okay, before I do that, let's just jump back to our FreeCAD manipulator workbench. We can select and delete that dimension. Right, what we now want to do is we want to find the location of that center point. So what we can do in order to do that, let's select the probe. Okay, so we say the center point, and let's go to this face. Okay, so now we must be careful. We have got the length, which is now from the center of the face to the center of that hole. That's ds. The x is 30 millimeters. That's the distance in the x direction. Y is 7. Okay, and z is 15 if you round that off, okay, to machine precision. 15, and z is the coordinate that we are interested in. Okay, so if I can show you here, yes, if you look at this, let's do this. Here we go. Okay, so how do I know that the z is the value that we want? Z is the blue axis. Okay, z is blue, x is red, and y is green. Okay, so y is perpendicular to the surface, x is obviously to the right, and z is in this direction. So our z component is 15 millimeters. So in other words, the distance from that face to the center of that hole is 15. Okay, we can do the same. Selecting that circle and that circle. So that distance is 320 millimeters. Okay. Okay, so what you see on the screen now is the 15 millimeter basic or theoretical exact dimension from datum Z to these two holes, and then the 320 between the two holes, or two sets of holes. What is also important is that there should be a dash dot line, or in this case now the section dash line is connecting the two holes, so we can clearly see that those two holes are at the same location. So the 15 indicates the location of both holes, and then I've got this dash dot line connecting those two holes, these two holes, as well as these two holes over here. So we can clearly see our dimensions relate to two holes. In this, the 320, and that's true also for the 15 millimeters. Right, so what we now want to do is go back to FreeCAD and measure the distance from datum Y to this hole, or these two holes rather, that vertical distance, and then the vertical distance between these two holes that are exactly the same as the vertical distance between these two holes. Right, so to do that, let's go to FreeCAD. We can select these distances that we've measured. Right, and then what we can do is with our probe selected, we select the circle and we select this face. Okay, and now what we must do, I can already see it's the x-axis. The x-coordinate is the one that we're looking for, which is also 15 millimeters. X is the red axis, and that's the direction that we are interested in. All right, and then if we click that hole and this hole, X once again is 60, which is the same as the total length, which is also 60, because those two are in line with each other in the X direction. So it's 15 from the edge and 60 between the two holes. Okay, and if you were wondering, this is obviously symmetric, so you can check that by saying, okay, what's the distance between that hole and this face? Okay, let's just see. There we go. X once again 15 millimeters. All right, so it's those two holes are symmetric. If you didn't notice that already. Okay, so now I've now indicated the 15 millimeter theoretical exact dimension from datum Y to these two holes, as well as the 60 millimeters. Now what I also just want to point out is the fact that I make my arrowheads. It's not that easy on my scratch or pencil pad, but you need to make it just basically what you want to do is make the line end a little bit thicker. It's not a very prominent arrow. It's not, yeah, it should be delicate. And with that, this base profile stage 1 drawing is completely dimensioned. Okay, we've got all of the dimensions necessary to manufacture this component. The one thing that I do want to just point out is what are the notes that we would add onto the drawing. So I'll show you the memorandum drawing. In this area over here, we will add notes specifying the material, the surface texture, the fact that sharp edges need to be removed, and unspecified fillet radii, as well as number 5 is the surface finish. If we were to paint or coat this component, we would specify it in notes. All right. So on this PDF, you can actually see the complete drawing with all the dimensions on the views of the drawing, and this is what I referred to earlier. The notes, the material is aluminium profile, PG30, 30 by 90, 8 slots. That comes from this description over here, from the supplier's description, and the others are very simply surface texture, RA 3,2 unless otherwise specified. So in other words, the faces, these faces that will get cut and the holes that will be drilled will have or need to have a surface texture of 3,2 micron RA. We need to break all unspecified sharp edges to 0,3 max by 45 degrees plus minus 5 degrees, and all unspecified fillet radii to be R 0,4 max. Okay, you could add, as I said, surface finish, and in this case the surface finish there's no specific surface finish that we want, so you could say surface finish none, for completeness sake. Yes, so with that said, that's the detail mechanical drawing for base profile stage 1. So next what we will do is dimension the side profile. What you see on the screen is the dimensionless detail mechanical drawing showing the 4 views, and we'll use these 4 views to add the necessary dimensions to specify all the features that we want. So in this case, it's obviously the length. We need to specify the length. And then in terms of features, there is this slot in the middle, and then the 4 tapped holes that we spoke about. All right. So first of all, let's decide to put the length dimension on this view over here. Okay, you could have put it here as well, or even here. It would also be okay. But we're going to put it on this front view over here. We'll put the 90mm reference dimension also on this view, and we will put the 30mm reference dimension on this view. To get the length of the side profile, we use once again the manipulator workbench in FreeCAD, and we can click this icon over here to get a length, and then select one of the edges, and there you can see it's 184 millimeters. So I've already added the 184 on the front view, and as you can see, I selected once again a tolerance of plus minus 0.5 millimeters or millimeter. You can go smaller, but not smaller than plus minus 0.2. Also, I don't think it's wise to go much larger than plus minus 0.5. So this is the maximum that I'm comfortable specifying. You will also notice the 90mm reference dimension on the front view, and if I scroll down to the right view, you will notice the 30mm reference dimension. So that was our first step, to dimension, to give the overall dimensions of our parts: the length, the width, and the thickness. The next set of features that we will dimension is the set of tapped holes that are visible, or that is visible on section AA. The 4 tapped holes that you can see over here. Now to do that, let's go back to FreeCAD. Let us once again delete that dimension, and if we orient it correctly, we can, as a matter of fact, select that, and it's 20 millimeters. So we've got the length. I selected this edge over here. Alternatively, what you could have done is click to activate the probe, and then select that circle and this circle over here, and there you can see for both it gives the length of, or the depth of, the tapped hole as 20 millimeters. So I've indicated the tap dimension. I've written the word tap M12 by 1,75 in 4 places. So I didn't mention it before, but the reason why I specifically write the word tap is because for the profile, there's no additional machining or hole to be drilled. It's simply a matter of threading the M12 thread into this already 10 millimeter diameter hole. So that's indicated, as well as the pitch of the coarse thread. That's standard. If you Google M12 thread coarse pitch, you'll get 1,75 millimeters. And then I write the words in 4 places, and that's because all 4 of these tapped holes are identical. And then the depth, as before, as with the base profile, I'm not specifying a tolerance. I'm just saying 20 minimum. You could specify a tolerance. If you do, I would specify it plus minus 0.5 or even plus minus 1 millimeter. But minimum is actually better in this case because if the manufacturer does tap the hole deeper than 20 millimeters, it is really no concern. It can't go too deep in this case. So with the 4 tapped holes specified, the only remaining feature that we need to dimension is the slot in the middle. Now I'm showing the slot in this view over here, the front view, and also in section BB. I clearly indicate that the slot goes all the way through the profile. And you can also see that, as a matter of fact, in this isometric view, there's a slot that goes all the way through. So we will dimension the length of the slot on the front view. We will dimension the width of the slot in section BB. Now, before we jump in with the dimensions, we need to take a few measurements. So in FreeCAD, with the manipulator workbench, let's select the probe, zoom in, we'll select that circle over there, and this circle over here. So the length of the slot is 100 millimeters. Now, what is the location of the slot? You can clearly see the slot is symmetrical. Okay, let me just delete that. This bottom length and the top length, they are equal. So let's quickly measure. If we click on the circle and we click on this face over here, okay, I missed, that was the wrong selection, so let's just try again. We click on the edge. You can notice the midpoint that's created. Make sure you select the face. Okay, and there we go. It's 42 millimeters in the Z direction. Z being the blue axis, that's what we are interested in, 42 millimeters. Okay, and just for reference or for reference purposes, let's quickly have a look. If we select that circle, we rotate and we select this face, once again Z 42 millimeters. So you can now see the tolerance or the dimension and tolerance that I've put from the bottom face to the midpoint of this arc, and then between the midpoints of the two arcs that define the slot, we also have that length. This is the correct way of dimensioning the length of a slot. Okay, you don't dimension to the edge of the arc, you rather dimension to the midpoint of the arc and between the two midpoints of the arc. Okay, now note the tolerance is quite loose, and that corresponds to the use or the need for this slot. There's definitely not a need to make it any more accurate than plus minus 1 millimeter, and 1 millimeter is a very relaxed tolerance. Alright, so our next step is to dimension the width of the slot, and in order to do that, what we can do is simply measure the radius of this arc here at the end, and that radius is 5 millimeter. So the width of the slot is in other words 10 millimeters. I've indicated now the width of the slot as 10 millimeter plus minus 0.2, a reasonably loose tolerance. I don't want to make the tolerance too wide or too large, because then we will cut into this portion over here, which I don't necessarily want to do. So 0.2 is a loose tolerance. It's easy to achieve, no problem there. Now going back to this front view, seeing that the slot can be have the slot width has a dimension of 10 and a tolerance of plus minus 2, we will not tolerance the two arcs at the bottom and at the top with a specific size. All we will do is we will say 2 times full radius. So what that means and implies is, dependent on what the actual width of the slot is, be it anything between 9,8 and 10,2 millimeter, the radius must follow the width of the slot. So that takes care of the width and the length of the slot. And this dimension also takes care of the location or position of the slot in a vertical direction. But what about the location or position of the slot in a horizontal direction? Now, in order to do that, there's an elegant solution that I want to suggest, and that is to define the symmetry plane of this 90 millimeter length as a datum, and then on this view we constrain the symmetry plane of the slot to be symmetric relative to our datum that we just discussed. What we've done here, the fact that the leader line of the datum box is in line with the 90 millimeter dimension implies that the symmetry plane of the view we are looking at is indeed our datum B. Going down then to the section view BB, we can see that I once again, in line with the dimension line, added a tolerance block with a symmetry symbol 0,4 relative to B. So we are constraining the symmetry plane of the slot to be symmetrical to the symmetry plane of the side profile to within 0,4 millimeters. The last thing that I want to add is I want to constrain the form of these two faces that will be cut from the standard or from a length of profile. So in order to do that, we need to define another datum. And what we'll do is, on this view, on the right view, we will define either one of these two surfaces as datum A. And then once that is done, we will come back to this view and constrain those two faces to be perpendicular to both datums A and datum B. Okay, so on the right view, I've indicated or defined this face as datum A. You can, and this is what this view illustrates, you can connect the datum leader line to the face itself or to the extension line of a dimension, but definitely not now in line with the dimension line, because we don't want to specify the symmetry plane as datum A. We want to specify this face as datum A. We could have also specified the opposite face. The same rules would have applied. Alright, so then going back to the front view, and very similar to the base profile stage 1, removed from the dimension line, separated from the dimension line, we've got a leader line with a tolerance block perpendicular 0,2 relative to A and B, and the same for this bottom surface. With that, all the features of the side profile have been dimensioned. This PDF shows the dimensions indicated on the detail mechanical drawing, and as before we have exactly the same notes as for base profile stage 1. The material is an aluminium profile PG 30 by 98 slots. Our surface texture is RA 3,2 unless otherwise specified. So what that means is when the supplier or manufacturer cuts the length of the side profile, that surface texture and the top surface texture need to be RA 3,2, and the same goes for the slot, the machining of the slot. Then very important, the unspecified sharp edges to be broken to a 0,3 max by 45 plus minus 5. This is specifically important for the slot because as I've mentioned at the beginning of the video, there's a fishing line that runs through the slot, and if you have sharp edges and the fishing line would make contact with any of those edges, you can get the scenario where the fishing line gets cut. Then lastly, all unspecified fillet radii to be R0,4 max. That's a standard note that I always put on a drawing. The one that I don't show here that you can also add is surface finish. If, for example, you wanted to paint or coat the side profile with a special paint or coating, then you would have said surface finish, whatever the paint is, or surface coating. But in this case, if you do add note number 5 here at the bottom, you would simply say surface finish none. So with that, the detail mechanical drawings of both the base profile stage 1 and the side profile are completed, and thank you very much for watching, and yeah, please have a look out for the next video, which will be on the memorandum of practicum 4. Thank you.